Welcome to this explanatory module on earthing, grounding, shielding, and intrinsic safety. These four concepts form what calls the invisible architecture of plant safety. Although most of these protective systems are hidden behind equipment, inside cable systems, or underground, but they play a vital role in protecting people, equipment, processes, and facilities. In industrial environments, electrical energy exists in many forms and at many different levels. Some hazards involve extremely high energy, such as lightning strikes or electrical faults. Others involve very small energy levels that can still create serious risks in explosive atmospheres or interfere with critical process signals. Understanding how earthing, grounding, shielding, and intrinsic safety work together helps engineers and technicians design safer and more reliable systems. We will explore each concept individually, understand its purpose, and see how they collectively protect industrial operations. Before looking at each protection method individually, it is helpful to understand the different scales of electrical energy that exist in a plant. This slide shows 4 levels of protection. At the macro level, we deal with megavolt energy sources such as lightning and major structural faults. These events are rare, but they can be extremely destructive. At the system level, we see normal power distribution systems operating between approximately 230 volts and 11 kilovolts. Here, the main concern is equipment faults and maintaining a stable electrical reference. Moving smaller, we reach the signal level, where many instruments operate using millivolt signals. These signals can easily be disrupted by electromagnetic interference, often called EMI. Finally, at the micro level, we deal with tiny amounts of energy measured in microjoules. Even these very small energy levels can become dangerous if they create a spark inside an explosive atmosphere. One of the most common sources of confusion in industry is the difference between earthing and grounding. Although the terms are sometimes used interchangeably, let's highlight the important differences. Earthing is primarily a safety function. Its purpose is to protect people and equipment by directing fault energy safely into the earth. Under normal conditions, the earthing conductor carries no current. It becomes active only when a fault occurs. Grounding serves a different purpose. Grounding establishes a stable 0-volt reference point for an electrical system. This reference helps equipment operate correctly and consistently. Unlike earthing, grounding normally carries return current as part of standard system operation. Because of this, grounding is essential for proper equipment performance. We need to understand a practical distinction. A piece of equipment may technically operate without earthing, but doing so would be unsafe. Grounding, on the other hand, is necessary for correct system operation. Earthing is the plant's macro-level defense system. Earthing is designed to protect structures and equipment from catastrophic energy events. These include large fault currents and lightning-related energy that could otherwise damage equipment or endanger personnel. The illustration represents how fault energy is directed away from equipment and safely transferred into the earth. By providing a controlled path to ground, dangerous voltages can be reduced and the risk of electric shock can be minimized. In industrial facilities, earthing systems form part of the overall safety infrastructure. They help prevent equipment enclosures and structures from reaching hazardous voltage levels during abnormal conditions. From a reliability perspective, effective earthing reduces damage that could result in costly downtime, repairs, or loss of production. Earthing protects people, structures, and equipment by safely dissipating fault energy into the earth. Let us see earth pit. This shows the main elements of an earth pit. The earthing electrode conductor connects the electrical system to an electrode that is installed in the ground. The electrode creates the physical connection between the plant and the surrounding earth. The electrolyte treatment, using salt or moisture to improve the conductivity of the surrounding soil, helps to lower overall resistance. Notice the formula shown as well. Total earth resistance is influenced by the conductor, the electrode, and the surrounding earth. The surrounding soil is identified as the largest variable because soil conditions can change due to moisture content, temperature, and composition. An effective earth pit must maintain low resistance so that fault current can flow quickly and safely into the ground. For maintenance personnel, this emphasizes why periodic testing of earth resistance is important. Changes in soil conditions can affect system performance over time. The effectiveness of an earthing system depends heavily on maintaining low resistance in the earth connection. Electrical safety is ultimately about protecting people. Let us study the danger spectrum of electric current flowing through the human body. The critical message is that very small changes in current can have major consequences. At less than 1 milliampere or 1,000th of an ampere, a person may simply perceive the current. As current increases, loss of muscular control can occur. This is sometimes called the let-go threshold, where a person may not be able to release a conductor voluntarily. Higher current levels can cause breathing difficulties. At even greater levels, ventricular fibrillation can occur. This is a dangerous disturbance of the heart's normal rhythm and can become life-threatening. The diagram illustrates that the difference between a mild sensation and a severe injury may be only a fraction of an ampere. This is why protective systems such as earthing and grounding are extremely essential. They are designed to prevent dangerous current from passing through the human body. You may refer to some of the standards applicable for earthing. IS 3043 mentions the code of practice for earthing. IEEE 80 provides the IEEE Guide for Safety in AC Substation Grounding, and IEEE 837 refers to the standard for qualifying permanent connection in substation grounding. We now move from safety protection to system performance. Let's study the concept of grounding now. Grounding is described as the system reference that establishes a 0-volt baseline. In practical terms, all electrical measurements and operations require a common reference point. Without a stable reference, equipment may not operate predictably. Measurements may become inaccurate, and system behavior can become unstable. Grounding helps electrical systems maintain consistency across generators, equipment, and connected devices. By tying components to a common ground reference, engineers create a more predictable operating environment. While earthing focuses on handling fault conditions, grounding supports normal everyday operation. Together, these concepts complement each other. One protects during abnormal events, while the other supports stable performance during normal operation. How grounding is related to human safety. Grounding plays an important role during fault conditions. Let us see the comparison of two situations. In an ungrounded system, a person may become part of the path through which fault current flows. This creates a dangerous touch potential. In the grounded example, fault current follows a dedicated low-resistance path. Electricity naturally tends to follow the path of least resistance. By providing a controlled conductive path, grounding reduces the likelihood that current will use a human body as its route to Earth. Protection systems should guide fault energy away from people and toward engineered paths specifically designed to handle it. In industrial facilities, this concept contributes significantly to electrical safety and helps reduce the risk of injury during abnormal operating conditions. The next concept is shielding. Shielding is described as the signal guardian. Its purpose is to defend important plant data from invisible electrical noise. Many industrial instruments generate extremely small signals. These signals may represent temperature, pressure, flow, or other critical process measurements. Electromagnetic interference, often called EMI, can introduce unwanted electrical noise into those signals. When this happens, measurements may become inaccurate and control systems may respond incorrectly. Shielding acts as a protective barrier around signal conductors. Instead of allowing interference to enter the signal path, the shield helps capture unwanted noise before it affects the measurement. Let us see how a shielded cable works. The outer polymer jacket provides physical protection for the cable. Beneath that, the shield surrounds the signal conductors. When electromagnetic interference reaches the cable, the shield captures much of that unwanted energy. A drain wire then provides a path for the interference to be directed away. An important point highlighted here is that the shield is grounded at only one end, usually at the receiving end. This practice helps prevent what are known as ground loops. We will revisit this concept in detail later. The key function of the shield is to collect external electrical noise and safely channel it away from the signal conductors. In industrial environments filled with motors, power cables, and switching equipment, shielding helps ensure that instrumentation data remains accurate and dependable. Accurate measurements lead to better control decisions, safer operations, and improved process performance. In addition to shielding, another important concept in signal integrity is the ground loop. A ground loop occurs when a potential difference, or voltage difference, exists between two grounding points in a system. Although both points are connected to ground, they may not actually be at exactly the same electrical potential. As shown here, the magnitude of this potential difference depends on factors such as the distance between the signal source and the amplifier, as well as the ground resistance at both locations. When equipment is connected through multiple grounding paths, unwanted current can flow through the signal circuit. This unwanted current can create electrical noise, distort measurements, and affect the accuracy of instrumentation signals. In industrial plants, where sensors and control systems may be located far from the control room, ground loops can become a significant source of measurement errors. Even small voltage differences can introduce noise into low-level instrument signals. This is one reason why proper grounding and shielding practices are so important. Engineers must ensure that signal grounding is carefully designed to minimize the possibility of ground loops and maintain signal accuracy. The key point is that not all grounding connections are equal. Differences in ground potential can create unintended current paths that interfere with system performance. Twisted pair wiring is one of the simplest and most effective methods for reducing electromagnetic interference, or EMI, in signal cables. Each twist in the cable forms a small loop. When external electromagnetic interference passes through the cable, it induces a voltage in that loop. However, because the direction of the loop alternates with every twist, the induced voltages tend to cancel each other out. This significantly reduces the overall effect of external EMI on the signal conductors. This principle is particularly valuable for instrumentation and communication circuits that carry small electrical signals. By reducing noise pickup, twisted pair cables help ensure that transmitted information remains accurate and reliable. Twist length is measured by the distance required for the conductors to complete one full 360-degree twist. Although twisting is a relatively simple cable design feature, it provides an important first layer of defense against electrical noise. In many industrial applications, twisting is used together with shielding to provide even greater signal protection. Together, these techniques help maintain data integrity and ensure reliable operation of monitoring and control systems. The final protection philosophy in this training is intrinsic safety. Intrinsic safety focuses on environments where flammable gases, vapors, or other explosive atmospheres may be present. There may be a condition that safe area is connected to a hazardous area. Equipment located in the hazardous area must be designed so that it cannot release enough electrical energy to ignite an explosive atmosphere. Unlike other protection methods that manage large amounts of energy, intrinsic safety works at the micro level. The objective is to keep energy levels extremely low. This approach allows instrumentation and sensing devices to operate within hazardous environments while minimizing ignition risk. Protection is achieved through control of energy before it enters the hazardous area. Intrinsic safety is therefore a preventive strategy intended to avoid ignition rather than manage the consequences afterward. There are three different approaches to explosion protection. At the center is the ignition triangle, consisting of fuel, oxygen, and a source of ignition such as a spark or heat. An explosion typically requires all three elements. The first approach is containment, identified as XT. The concept is to allow an internal explosion to occur while ensuring the enclosure contains the blast. The second approach is segregation, identified as XP. Here, the goal is to remove access to fuel or oxygen. The third approach is prevention, identified as XI, which stands for intrinsic safety. Rather than containing or isolating hazards, intrinsic safety prevents the release of sufficient ignition energy in the first place. This preventive approach targets the ignition source directly by limiting energy levels. Different protection philosophies attack different parts of the problem, but all aim to prevent catastrophic events in hazardous environments. Let us see the concept of safety barrier now. The barrier sits between the safe area and the hazardous area. Its function is to enforce absolute energy limitation at this boundary. This barrier can be a non-galvanically isolated barrier, that is a Zener diode, or galvanically isolated barrier, that is a transformer. In simple terms, the barrier controls the amount of electrical energy that can pass toward equipment in the hazardous zone. If abnormal conditions occur on the safe area side, the barrier helps ensure that excessive energy does not reach the hazardous area. The diagram illustrates this critical separation between the two zones. By managing energy at the boundary, the system reduces the possibility of producing an ignition-capable spark in the hazardous environment. This makes the safety barrier a crucial component in implementing intrinsic safety principles. Let us recall all four protection disciplines into one integrated safety architecture. First, earthing directs high-energy events such as lightning safely into the earth. Second, grounding establishes a common reference through an equipotential grid, helping systems operate correctly and safely. Third, shielding protects sensitive data signals from interference, ensuring accurate communication and measurement. Fourth, intrinsic safety protects sensors and devices operating within hazardous zones by restricting available energy. Although each discipline addresses a different type of risk, they work simultaneously throughout the plant. It is important to remember the ultimate purpose behind every engineering protection system is human safety. We must strive to design for the fault, protect the signal, and secure the environment. Electrical faults may not occur every day, but systems must be prepared when they do. Signals must remain accurate so that operators and automation systems can make correct decisions. Hazardous environments must remain safe so that ignition risks are controlled. Earthing, grounding, shielding, and intrinsic safety are not simply technical requirements. They represent layers of protection that support safe and reliable operations. Hope this video explains to you the concept. Thank you so much for your time.